Okay, so good morning, everyone. So first, thanks to Sebastian and all the other organizers for this really nice conference on inflation and for inviting me to present my work. And I will talk about some new advancement in stochastic inflation and stochastic delta M formalism, and also how we can try to implement stochastic inflation on stochastic trees and use this tool to study primordial black hole formation in the early universe. Okay, so to start, let me just introduce what is the simplest inflationary scenario we can have in mind. That is a single feed slow roll model. And even in this vanilla scenario, we still do not know what the inflationary potential exactly looks like. And this is mostly due to the fact that with cosmological observations that mostly are given by the cosmic microwave background, we only access a restricted regime of rather large scales. So in terms of inflationary evolution, this encompasses about 7 e-folds over the at least 60 e-folds of inflationary expansion. And on this case, we know that perturbations are small at the level of 10 to the minus 5 for the comoving curvature perturbation. They are almost Gaussian and almost scale invariant. And this constrains the shape of the inflationary potential to be of plateau type. But the rest of the inflationary potential is rather unconstrained. And so we can imagine to have some features at small scales, close to the end of inflation, that could subject the inflaton to departures from slow roll or to large quantum diffusion effect. And in these cases, we can have an enhancement of the curvature perturbation from this 10 to the minus 5 value to values of order 1. And if this is the case, then we can have formation of primordial black holes in the early universe. So really quickly, since they were already introduced, primordial black holes are black holes which could have formed in the early universe in a non-stellar way. And why we are interested in them is that if they exist, they may have important astrophysical and cosmological roles. And here I've just listed a few. They could be a fraction or even the totality of dark matter in this asteroid mass range. They could also explain some of the merging events observed by gravitational wave collaborations. They could also see supermassive black holes in galactic nuclei. They could also have some role in generation of cosmological structures. And as early universe cosmologists, we are interested in primordial black holes because, as we have seen, they are formed at small scales. And so, in some sense, they give access to some scales of inflation that we cannot access with the cosmic microwave background or large scale structures. And also, as we will see with this talk, also they are a place to look for some effects from quantum diffusion during inflation. And in a few words, primordial black holes are formed from the collapse from peaks of density perturbations that are generated in the early universe. And the idea is the following. So if we have some enhanced curvature perturbation zeta, then those could induce some overdensities in the primordial plasma when inflation is over. And if those overdensities are larger than some critical threshold that we can assume to be of order 1 for simplicity, they can collapse and form primordial black holes when they re-enter the Hubble horizon during inflation, after inflation, sorry. And this typically happens in a radiation-dominated era if we assume a standard OP band cosmology. And the goal of my talk is to explain how we can describe the properties and the statistics of these large fluctuations that can give rise to primordial black holes. And let us do a step back and consider what is the theory that we use in the early universe to describe fluctuations. So this is cosmological perturbation theory, and this is based on splitting the degrees of freedom that are relevant during inflation, so the metric degrees of freedom and matter degrees of freedom, so only the inflaton in the case of single feed inflation, into a homogeneous and isotropic part that only depends on time, so this is the background. And on top of this background, we have small fluctuations that also depend on space that are quantized. And this gives rise to a quantum field theory in curved space-time that is the framework we use to do computations for the expectation values of those quantum fields, and then we compare those expectation values with correlators we extract from data. And of course, this perturbative picture is well valid at CMB scales, where we know that density fluctuations are constrained to be small, but this can be broken at small scales, especially if you have large fluctuations that can collapse and form primordial black holes. So this means that we need to go beyond perturbation theory and work with some non-perturbative framework. And a possibility, as we have seen introduced also yesterday in other talks, is given by the separate universe approach that basically describes the universe at large scales as a collection of independent, locally homogeneous and isotropic patches of Hubble size that evolve according to background equations of motion, but starting from different initial conditions. And in this separate universe picture, the curvature perturbation is identified with the local amount of expansion in those patches. So this is what is called the delta N formalism. And now, if we have large fluctuations, what we also may want to do is to include some back reaction. And this is possible if we describe those amount of expansions and their statistical properties using stochastic inflation. That, in a really few words, is an effective theory for quantum fields during inflation, so for the inflaton itself, that are cos-grained above the Hubble radius, in a way that subhorizon modes are still small amplitude modes that are still described in cosmological perturbation theory. But on super-Hubble scales, we replace cosmological perturbation theory with this effective theory. And because during inflation, the comoving Hubble horizon shrinks, what we have is that those subhorizon modes constantly they cross the Hubble radius and they join the cos-grained sector of the theory. So they act as an effective contribution to the large-scale fields. And as a consequence, this coarse-grained field then follows a stochastic classical theory that is described by Langevin equation that we see here. So we have the red term is the usual classical drift term, is induced by the gradient of the inflationary potential function. And then we also have a green term where we see a noise that is the effect of this quantum diffusion from small-scale fluctuations. And the properties of this noise depend on our cos-graining procedure. So if we consider a sharp window function in Fourier space, then the noise will be white. And also they depend on how we describe our theory in the subhorizon regime. So if we use cosmological perturbation theory at leading order, then we have a quadratic theory. So we have a Gaussian theory, and the noise will be a Gaussian noise. So in what follows, we will consider this psi to be a white Gaussian noise with vanishing mean and unit variance. Okay, so now, as I said before, we want to combine those two steps and describe those amount of expansion in the separate universe framework with stochastic inflation. And then this gives rise to the stochastic delta N formalism. And the idea is that if we start from some initial condition in field configuration, then because of this quantum diffusion, we can have trajectories with different durations up to the end of inflation. And this duration now becomes a stochastic quantity. So it's described with its own probability distribution function that is called first passage time distribution usually. And this because we are interested in the first time the end of inflation hypersurface is crossed. So it's a first passage time in a stochastic analysis. And this distribution can be obtained by solving what is called the joint Fourier-Planck equation. And then once we have solved for these statistics of n, we can infer the statistics of this coarse-grained zeta, and thanks to the delta N formalism, and this is a non-perturbative result. And in general, we can always expand this first passage time distribution with, as a sum of decaying exponential functions with some decay rates that are ordered according to this hierarchy. And if we look at large values of n, so if we're interested to the tail of the distribution, then we can approximate this sum with the first term only. And this implies that we get exponential tails that are strongly non-Gaussian, and also they describe a non-Gaussianity that we cannot obtain in perturbation theory. And as we have seen, this is relevant for primordial black holes because they are events that are rare, so they are sensitive to tails. And for instance, if we want to compute their abundance with a simple Press-Schechter approach, so we just integrate the relevant cosmological fields above some critical threshold, then we find results that are orders of magnitude of difference if we use an exponential tail distribution instead of a Gaussian one. So this is relevant for the prediction of abundances, also in light of constraints we have on primordial black holes. And so this is also relevant for inflationary model itself. Okay, so This is a bit the usual, the standard stochastic delta formalism. This has been applied in many models in which quantum diffusion is at play at small scales. But now I would like to introduce some challenges that we have to face if we want to go beyond this usual picture. And in practice, what we do when we consider a single Langevin realization is that we follow a word line up to a final patch on the end of inflation hypersurface. And if we do this many times, we have seen that we can reconstruct these non-perturbative statistics of the coarse grain zeta. But we may ask if the information on how these separate universe patches are the information on the spatial arrangement of those patches on the end of inflation hypersurface is lost or not. So in practice, we may want to ask if it's possible to describe spatial correlations in this formalism. And why this is relevant for some cases, for instance, if we want to extend the formalism to coarse graining not at the Hubble scale at the end of inflation, but at some arbitrary scale that could, for instance, embed more than one patches. And this is useful for primordial black holes if you want to study their mass functions, and also if you want to study statistics of other fields like density contrast or compaction function that are usually used to study the fate of overdensities and assess if they collapse or not in primordial black holes. And also this is really relevant if you want to study clustering properties of primordial black holes, so how they are spatially distributed in space, and what is the role of these non-perturbative non-Gaussianities, so what is the impact of quantum diffusion on their spatial distribution. And so at the end, the main question is, can we encode in the formalism some information about distances on the end of inflation hypersurface? And we can imagine that in this separate universe framework on which we implement stochastic inflation, the information on the distance between two patches on the end of inflation hypersurface is retained in the time at which the word lines they emerge from become independent. And so this means that we can extend this formalism beyond one-point distributions and also beyond coarse graining at the Hubble scale at the end of inflation. And to better understand what I mean, we can consider this schematic diagram of inflation. So time goes from bottom to top. We can start from a single patch, pi 0, and then it expands, and at some point inflation ends, and the blue line is the end of inflation hypersurface. And we can consider 2 points, x1 and x2, at some distance r. And we are interested in coarse graining the perturbation field around these 2 points in some regions of sizes r1 and r2. So if we consider the word lines that are that ends up inside those 2 regions, then if we go back in time during inflation, at some point we see that they all are emerging from the same Hubble patch. For instance, we call here P1 and P2. So this means that at some point their distance is smaller than the Hubble radius. And this allows us to coarse grain at arbitrary scale in the formalism. And again, if we consider all the word lines that end up in the joint region between these 2 points, they are all contained in the same Hubble patch that is called P star. We can refer to this as a joint parent patch. So in practice, this means that these word lines share some common history, and it's really this common history that carries the correlation that we want to describe. Now, the challenge is that our statistics, so our computations, will depend on field configurations in those splitting patches. And those field configurations are not easy to reconstruct because in the stochastic picture, we are really different from a classical one. So in a classical setup, there is a one-to-one correspondence between scales and field values because we have a single classical trajectory. But in the stochastic setup, this relation between scales and field values is blurred by quantum diffusion. So a first attempt was made in these papers where those field values at splitting patches were associated to field values at some fixed backward number of e-folds, where backward means just counting e-folds from the end of inflation back in time. And of course, those fields are stochastic, so they have their own probability distribution that is written there. It's called backward distribution. And then this allowed to find a prediction for the statistics of coarse-grained field at arbitrary scales. And this also allowed to find some predictions for the mass function of primordial black holes that here is plotted. And this is the case derived in a model where there is a flat region at small scales on the inflationary potential function. So it's fully dominated by quantum diffusion. And more recently, we tried to go beyond this picture and propose an alternative way to link scales and field values during inflation that is even more involved, because we propose that this relation is really encoded in the separate universe structures of a universe that undergoes stochastic inflation. And again, let us consider this, sketch of an inflating universe. So we start from a single patch, the orange one, pi 0, and then time goes from bottom to top. So as time goes on, this patch will grow in volume, so it will give rise to new patches and so on and so forth. And at some point, inflation terminates, so we have the blue line. And so at any time, we can consider a certain patch, P star, with some field configuration, phi star. And this will produce a certain volume on the end of inflation hypersurface that is the sum of the volumes of the purple circles. And now, if we imagine to have an observer on the end of inflation hypersurface that is measuring volumes, then you could ask what is the volume that is produced from this patch. And this volume can be computed in this way. So it's just the integral of over all the world lines that are emerging from this patch of this exponential free n. And n, we know how to compute it because it's a forced passage time. But this quantity is not easy to reconstruct because all the world lines are not independent, but they are independent only after they split. And now if we ask what is the probability of field configurations phi star, knowing that a certain volume has been produced at the end of inflation, then it can be expressed with the second expression written here. So it contains the volume distribution. Then there is the probability to cross this field value phi star, starting from the initial condition, and then there is just a normalization factor. So this shows that the relation between scales at the end of inflation and field configuration is really depends on the evolution of this inflating universe. Let me just introduce this quantity W, which is just the volume average number of EFOs starting from this patch. So basically, we measure the number of EFOs from the patch P star up to each of these purple circles, and then we perform a spatial average. And this is useful to reconstruct the curvature perturbation. And finally, with all these ingredients, we managed to find an expression for the one-point statistics of the coarse-grained curvature perturbation at arbitrary scale that is free from from other approximations than the ones that we use already in the stochastic delta n formalism. And it contains some green quantities that we know how to compute. They are solutions of Fokker-Planck equations, adjoint Fokker-Planck equations, but unluckily it also contains some red quantities, so volume distribution of this W that are not really easy to compute analytically. And a similar expression can also be found for the two-point statistics of zeta at two different locations. And before moving to some results, I just want to mention another thing that is volume weighting. We know that different regions of the universe undergoes inflation for a different amount of EFOLs, and if you have large quantum diffusion effects, those amounts could also vary a lot. So if now we consider a perspective of some observer on the end of inflation that is performing some measurement, then he encounters more patches in regions that inflated more. So in some sense, those regions contribute differently to ensemble averages he is performing. And so since this spatial average is basically a volume average, this means that statistics that an observer has a variable are naturally volume weighted. So in some sense, this means that we need to volume weight the distribution we use to define observable quantities. So we can introduce a volume-weighted version, for instance, of a forced passage time distribution. And so also the distribution of the curvature perturbation should be volume-weighted. But now this introduced an issue because, as I said before, the forced passage time distribution has some exponential tail with some decay rate lambda. And if this lambda is smaller than 3, then the integral in the denominator is not convergent anymore, so it's not well defined. And this is really an appearance of an eternal inflation problem. So we are not able to solve it in this formalism, but it's important to have it in mind. And in the following, we will just work with scenarios in which this problem is not encountered. Okay, so as I said before, now we will move to some results, but as I said before, it's really difficult to reconstruct analytically those distribution of volume at the end of inflation and of this volume average number of e-folds. And so what we did to find some results was to work in what we call the large volume approximation, where basically we replaced the integral in the first line with a stochastic average. So in some sense, we replaced the volume with the mean volume. And in this scenario, just to understand it better, the volume distribution is just a direct distribution centered around the mean value. And with this approximation, we found some results for one-point statistics of zeta, cos-grained at arbitrary scales. Those are just some plots we obtained in a model with a flat region at small scale, in a model of inflation with a flat region at small scales, and in the bottom line with a small tilt, where different colors are just different cos-graining sizes. And what I want to emphasize is that even in this case, we still find exponential tails appearing in those distributions. We did this also for two-point statistics. This was the same slide that Juan showed before. So on the left, we have some results from analytical approximation of two-point distribution of zeta at some fixed physical distance. And on the right, we have some results from numerical simulations, so Langevin simulations. And also in this case, as we can see from this bottom right panel, where we have some slices of this distribution, we have exponential tails, also characterizing two-point statistics. And why we are interested in two-point distribution is that we can try to reconstruct some clustering properties of primordial black holes and see how those are affected by quantum diffusion. And in particular, we can reconstruct this reduced correlation xi, which is basically the ratio between the two-point probability of having two primordial black holes at a certain distance divided by the single one-point probabilities minus 1. And this is an indicator of deviation from Poisson clustering that is expected if primordial black holes form from peaks of Gaussian fields. And what we found is that on the tail, that is the regime interesting for primordial black hole formation, the two-point distribution can be written as the product of the two single one-point distributions, and then there's a factor, the green one in the box, that only contains parameters of the inflationary model we are considering and cos-graining sizes, so basically masses of the black holes we are looking at. And so these peculiar structures on the tail means that if we compute the reduced correlation does not depend on the formation threshold. And this has two main consequences. So the first is that this is an indicator in some sense of a sort of universal clustering profile, not only for primordial black holes, but also for all structures that are born in the tail of the distribution. And also, if we consider Gaussian clustering in the large threshold limit, this is always suppressed by the ratio between the square threshold and the fit variance. And so we expect clustering to be always larger when we include quantum diffusion. So of course, this is just a preliminary result in some sense. It's also based on those approximations I mentioned to those large volume approximation to link scales and field values. And this is why we were pushed to go beyond, and this will be the topic of my second part, in which we considered an alternative way to study those problems. And this is based on trying to implement numerically stochastic inflation on stochastic trees, modeling the inflationary expansion as a branching process. And this is based on some work with those collaborators that I think are all in this room. So just as a reference, we always consider a single fit slow roll model of inflation. So this is the Langevin equation we have to keep in mind. We work with a white Gaussian noise, and cos-graining is performed over those Hubble patches of this size sigma h to the minus 1, and sigma is the usual small parameter of stochastic inflation. So we can imagine to start at time equals 0 with a single Hubble patch I. Then, as time goes on, this patch will grow, and so at some point, after a time that here is log 2 over 3, because we consider a binary process, will split into patches, L and M, that are independent. So this means in practice that we start with some field configuration in node I, and we perform two large generalizations to find field values in patches L and M. And they have no future causal contact. So in this way, the separate universe picture we work with is implemented. And this structure is an elementary vertex that can be iterated in a recursive way up to generate a whole stochastic tree that is made of nodes and branches. And if inflation never stops, then the tree will grow indefinitely. But in practice, we know that inflation has to stop. And this happens in the final nodes that we call the leaves of the tree, and that are the green patches here. And stochastic trees of this type can be generated, simulated efficiently numerically, because each vertex gives rise to a substructure that can be processed independently. And we have developed a code that is called forest, that is also available, that takes as an input an inflationary potential function, its derivative, some boundary condition for the field evolution, and it generates and also explores a large number of trees to deliver relevant statistics that we need for cosmology and also for primordial black holes. Okay, so once we have a tree of this type, then it's easy to reconstruct all the quantities that I've introduced before. For instance, if we have a certain node I in red that generates a set of leaves in green, then we can easily compute what is the physical volume which is emerging from this node. It's just the sum of the volumes of those leaves. We can compute this W quantity, which is just the expansion from the node I that we average over all the set of child leaves. And then if we imagine that this tree is the observable universe of a certain observer, then if we want to compute the curvature perturbation in this scenario, then this will be given just by the number of equals from the root node, which is the node 1, up to a final leaf, for instance, the leaf Lj. And then we have to subtract this W1, which is just the volume averaged expansion over the whole observable universe of this observer. And this can be generalized also if you want to cosgrain the curvature perturbation over a set of leaves, for instance, the set of leaves that is descending from the branching node I. Okay. Stochastic trees are also useful to study primordial black hole formation. And just some comments. So we know that primordial black holes form in regions of high curvature. But we also know that using the curvature perturbation zeta is not always the best quantity to use, because it's defined with respect to some observer, and also it's not local. We see here that it depends on this W1, that is the volume average over the whole observable universe. So it means that it depends on averages over regions that are really far from the region we are interested in. And this is why usually other fields are considered like density contrast or compaction function, because they are more local tracer of the high curvature regions. And in stochastic trees, what we use is a proxy for the compaction function as that is the coarse-shelled curvature perturbation. And this is based on idea proposed in this work by Van Sol and Yuichiro Tada. So in practice, what we do in stochastic trees, if we imagine the elementary vertex, we consider the curvature perturbation in a certain child node, for instance, in node L, relative to its local environment I. And we define this quantity as the difference between the curvature perturbation in node L and in node I. And why it's called coarse-shelled curvature perturbation is because we can picture the regions emerging from those nodes as two concentric spheres, and then this quantity is just the curvature perturbation that is averaged in the shell between those two regions. And now we consider that the nodes for which this coarse-shelled curvature perturbation is larger than a certain threshold will collapse into primordial black holes. If we consider radiation dominance and a threshold for the compaction function of 0.5, then the threshold on this coarse shell is just 1/2 the logarithm of the ratio of the volume of the parent over the volume of the child. And what we find is that primordial black hole formation happens at most asymmetric nodes. And this means in nodes where the expansion generated by the two siblings is very asymmetric. And so in some sense, this core-shelled curvature perturbation can be seen as an unbalance index in the tree. Okay, so in the remaining time, let me just move to some results. And as an application of stochastic trees, we just consider this really simple toy model that is called a quantum well. So it's a region that is flat at the end of the inflationary potential function. So its dynamics is driven by quantum diffusion. There is only one parameter that is relevant, that is this mu square parameter, that is an indicator of quantum diffusion. So if mu increases, we expect to have more effect from quantum diffusion. And in particular, there is a critical value of this mu, which is written in the bottom, for which we have eternal inflation. So for values of mu that are larger than this value, basically the mean volume is not convergent anymore, so our stochastic trees grows indefinitely. And then what we do is to work with parameters that are below this critical value in what follows. Okay, so what we did first is simulate a large number of trees of the order of 10 to the 10, 10 to the 11 in this model, and then trying to reconstruct some statistics over those trees. So here I'm showing some forward statistics of the volume and of the volume average number of e-folds. Different colors are different values of this mu parameter. So we see that as mu increases, as we expect, the tails of those distributions become heavier, and this is expected because mu is an indicator of quantum diffusion. We have a first regime that is a power law behavior, and then we have, again, exponential tails, also in those distributions. And in particular, if we focus on the volume distribution, we see that it has a power law behavior with a power minus pi half, and then there is some exponential tail. And if we go closer to the critical value for eternal inflation, then we get a pure power law. So there is no anymore exponential tail part. So, and this corresponds to the black dashed line in the plot. And interestingly, this is expected from bacteria models that are Galton-Watson processes. So those are models that are studied a lot in biology, for instance, to study bacteria reproduction and extinction. And in those cases, in our case, bacterial non-extinction corresponds to eternal inflation. We may also want to be interested in reconstructing the statistics not only over trees, but over the entire over the whole leaves of the entire tree population. And this is, for instance, a plot of the volume-weighted distribution of the number of e-folds. So this is linked closely to the distribution of the curvature perturbation theta. Again, different colors are different values of mu. And in dashed, we have analytical results that for this model is exact. And we find an excellent agreement. And this is not trivial because, firstly, the different realization over which we reconstruct those statistics are not completely independent, because if they belong to the same tree, they share some correlation. And this agreement is also really useful because it serves as a test of our numerical procedure, and also it serves as a test of this volume weighting procedure that is at the basis of all the approaches that we have to work out to reconstruct statistics of cosmological observables. Okay, so finally, as I said before, we can use stochastic trees to harvest primordial black holes. So this is a tree realization that we obtained in this model that contains 5 primordial black holes that basically corresponds to the collapse of the nodes that are circled in red. And what here I want to emphasize is that when we check for primordial black hole formation, we start from the bottom, so from the end of inflation hypersurface. And then on each branching, so in each vertex, we check if the condition of PBH formation is satisfied. And then we climb up the tree up to the root. And if we find a new node in which the condition is satisfied, we basically retain this node and we discard all the internal structure. So in some sense, since we only keep the highest or the oldest nodes in the PBH inventory, this is a way to naturally account for the cloud-in-cloud problem, so for basically the formation of, nested formation of primordial black holes. And this problem is naturally accounted for in stochastic trees. Those are some plots for distribution of primordial black holes in this model. So on the left, we have the fraction of the universe at the end of inflation that will collapse into primordial black holes as a function of mu. So results from simulations are the blue dots, and then in orange we have a prediction that is based on using the curvature to perturbation with a Press-Schechter approach to compute the abundance. So we see that as mu increases, the fraction of the universe in primordial black holes increases, and close to the critical value, so close to 0.9, almost all the universe is made of primordial black holes. And what is remarkable here for us is that if we compare those two curves, they have the same behavior, and also the difference is not so large. So this means that the estimates that usually are done in the stochastic delta formalism by using the curvature perturbation and the Press-Schechter approach can be considered in some sense reliable for the order of magnitude of abundances in inflationary models we are considering. And on the right, we have the mass function of primordial black holes in this model. Again, different colors are different values of mu. Again, those distributions are characterized by power law behavior and then exponential tails. And as mu increases, we see that basically we expect formation of primordial black holes almost at all scales, and then at all scales. And okay, this alpha is not computed analytically, it just comes from trying to fit those distributions. And okay, finally, I just want to show a final tree. This is based on some work in progress we are doing at the moment. And basically, what I presented so far is based on trying to use this core-shelled proxy for the compaction function. But we can try to do something better and try to really reconstruct something that is closer to the compaction function from stochastic trees. And in particular, we can try to reconstruct this quantity 1 plus r zeta prime from stochastic trees. And this is possible because stochastic trees give access to a certain volume that is comprised in a certain region. And we can try to, and we can then discretize those expressions. And this can be accessed from trees if we compare free generation of nodes. So basically hierarchy of free nodes, and not only two as we did with the core shell proxy. And so this can be a better estimate for the compaction function, and also this can be used to assess if perturbations in a certain nodes are of type 1 or type 2, where type 1 and type 2 refers to the behavior of the error radius of those perturbations. If we look just at the sign of this 1 plus r zeta prime, which is basically the derivative of the error radius with respect to the spatial coordinates. And for instance, here we have some red and black nodes that corresponds respectively to nodes where we have type 2 in red or type 1 perturbations. Okay, so this was my last slide before conclusion. Okay, so in my talk, what I wanted to emphasize is that if we have large perturbations that are generated during inflation, then those should be described with some non-perturbative methods, and one is given by the stochastic delta formalism. And a characteristic signature of it is the presence of non-Gaussian exponential tails, and this is relevant for primordial black holes. And we can also extend the stochastic delta formalism to beyond one-point statistics. But we have seen that as soon as we want to go beyond the standard picture, then we are forced to do many approximations and mostly to relate scales or distances at the end of inflation and field configuration when those scales emerge from double radius during inflation. And as you have seen, an alternative way that is efficient is trying to simulate stochastic inflation on stochastic trees. modeling the inflationary expansion as a branching process. And statistical properties of curvature perturbations and other fields are naturally embedded in the tree structure. And also we can use stochastic trees to study primordial black hole formation in the early universe. They also directly address the cloud-in-cloud problem. And a generic result is that we found power law behavior followed by exponential tails in all statistics we reconstruct over the trees, over the leaves, and also on the mass function of primordial black holes, at least in simple toy model we considered. And some open challenges that still we need to face, and I listed here some. So we have seen that this volume weighting procedure leads to an eternal inflation problem that still we are not able to solve. But we also know that local observers at the end of inflation have access to a finite region around them in which we know that inflation has terminated. And so we could wonder if a formalism that is only expressed in terms of backward quantities can help to avoid eternal inflation. And in this sense, there are nice recent work on a time-reverse formalism of stochastic inflation developed by Baptiste, Blachier, and Christophe Ringevall that could be maybe useful in this sense. Another open challenge is how to go beyond analytically and try to reconstruct those distribution of volume and of volume average number of IFOs that enters in our statistics. And a possibility is indeed to map the inflationary expansion with those bacteria model of inflation. This has been done in the past in a series of work where basically creation of new inflationary expansion has been considered in analogy as a process where bacteria can reproduce and then die at some end site that corresponds to the end of inflation in our case. And this is what is called in a statistical analysis a multi-type Galton-Watson process, and maybe is the route to try to find some analytical results for those distributions. And finally, what I presented was based on a simple toy model and on a slow roll, but we can extend the use of stochastic trees to ultra slow roll. And also I focused only on one-point statistics, so on abundances of primordial black holes. But the information that is embedded in stochastic trees also allows us to reconstruct real space correlations of curvature perturbations. So in some sense, this can be used to extend the use of stochastic trees to also reconstruct their clustering properties and also power spectrum and multiple point statistics directly from them. And on the majority of these points, I'm working with I'm lucky to work on this with my collaborators that are listed here, and we hope to have some results on this soon. And I thank you for the attention.
Thank you, Chiara. Do we have any questions? I think we have time for a few.
Okay. I want to confirm that you mentioned ultra slow here, but your potential, which is like flat plateau, look like that is actual slower inflation, no?
Yes.
What's the difference?
Yeah. So what we did there is to assume a slow roll. So basically, we just evolve our Langevin equation for the field value. We don't consider also some Langevin equation for the velocity of the fields. So we remain with the slow roll approximation. We have some work in progress in ultra slow roll, and with ultra slow roll, I mean that we consider also some initial velocity that is maybe coming from a previous phase, and also consider the impact of this velocity on our on the model. And on this, we are working at the moment.
So you ignore the classical drift, you mean?
Yes, we had some.
I see. I think that's the reason why you have this eternal inflation thing. And
So
if you have classical drift, then the eternal inflation regime will be.
Yeah, it's a bit. So eternal inflation at some point is not only linked to this. So even if you have some velocity or some classical drift, at some point you encounter like eternal inflation regime on the tail, because you always have exponential tails appearing at some point.
Okay. Thank you.
Hey, Hey, thank you very much for the nice talk. Yeah, so since you mentioned the talk, the work by Dubovsky, actually I'm wondering about what's the difference from your, stochastic tree from the old works of Sergei Vinitsky and, Dubovsky's work? Is it just rephrasing the, bacteria-like model in the language of delta N, or it's more than that?
Okay, yes, I think indeed it's pretty similar, though I don't know well all the works. But yes, probably it's a bit of rephrasing of what they work in the language of delta N formalism, yes.
Okay, another question is related to Shi's question, but how did you identify the PBH which is harvested, which is quite similar to the eternal inflation case, right?
Yes.
And then, what's the condition to identify that this bacteria corresponds to the PBH?
Okay, no, but here, so bacteria is just, so basically here, this model is like a one-dimensional model. So you have this line, with some positions that correspond.
Yeah.
And basically, this creation of new bacteria at each time step corresponds to creation of new patches.
Yeah, I
and
understand.
This is useful to reconstruct this volume distribution, probably, and this distribution of EFOLs. Then for primordial black holes, probably is not useful, because this bacteria is more useful for the dynamics. And then to study PBH formation, probably, I don't know if this can be useful or not.
Also, based on their language, I think the one which does not go into the eternal inflation is the one which reaches this boundary,
that reaches this
right?
end site.
And then I guess I was imagining that the one which corresponds to PBH is the one which stays long term but still ends up with the absorbing boundary.
Yes, if we imagine that primordial black holes form when we have a large curvature perturbation, then it's, yes, those are those realizations in which you take more time to reach this end site. Yes.
Okay, so you put some criterion for the length of the...
Yes, then if we use compaction function or other things, then this is more complete.
Okay, thank you very much.
So I think now we go on for a coffee break. I propose that we reconvene at 11:15, and I think we have a bell basically to ring you. So thanks again for Chiara, and